up? This is Happy Potato speaking, and this is not procrastination. This is part 1 of section 2 of the Edexcel IGCSE Physics Syllabus called Electricity. Ooh. As we discussed in the beginning of section 1, from this section and for all physics in general, we need to know a few basic units. The ones I'm talking about now specifically are amperes, or amps, coulombs, joule, ohms, which have that interesting symbol, volts, and watts. It can be tricky sometimes to make sure that all your questions are calculated in the right units, so you have to be extra careful when reading the information given to you in the question. To make sure that you gain the highest mark possible, try and make sure that you lose a minimal amount of marks to not changing the unit in the question. And I'd just like to comment that really using YouTube channels such as this one can really guarantee you to getting an A star in any single topic that you want in physics, chemistry, biology. I guarantee if you watch every single video, understand, ask questions if you don't understand, and really work hard at it, I guarantee there's no way you can't get an A star. Right, so mains electricity. So what are the dangers of mains electricity? Well, let's see. There are frayed cables. So that is my interpretation of a frayed cable. Where the insulation is worn down, exposing live wires. So these have sparks coming out. So look, something like that maybe. And these sort of obviously give the risk of being electrocuted. You also have long cables, which are literally just long cables, which are at a higher risk of being damaged since there's more to be damaged. And there is also the fact that they have more resistance. We'll cover more about resistance later on, but right now all we need to know is that the longer the wire is, the more resistance they have, which makes them more at risk of overheating. Also, we have the problem with damaged plugs, like this. These sort of three-pronged ones you get with like old laptops and whatnot. When these get damaged, like this, it can really pose a threat to anyone, possibly. And if one of these isn't connected properly to the connections, let's say it's not connected here, then that means that perhaps the extra charge in the case of a power surge might not be able to flow through and become earthed, and that may cause the appliance to become damaged. We also have water around sockets, which is also a major problem. So if we just draw like it's dripping like that, then hopefully that communicates that water is not a good idea around sockets. See, it's dripping with water. And basically the problem with that is, well, water conducts electricity, and that can cause energy from the circuit to flow through the water, creating a risk of fire and electrocution. And finally, pushing metal and pushing electrically conductive objects into sockets. If you have a socket here, and we have someone who feels like it's a good day to, place a fork inside, then we also have a very funny anecdote to tell, because they are now dying in hospital. Okay, here's some helpful definitions you need to know for this section, that you definitely need to know for the exam. First of all, we have insulation. And this is when a non-conductor of electricity, something like plastic or rubber, is used as the casing for a conductor or an appliance rather than another conductor. So this is the plastic in a wire. This is like when you remove the plastic on a metal wire. This is the plastic casing, which is a non-conductor. Move that out of the way. Non-conductor. And this is the metal, which equals a conductor. And the plastic is the insulation. A non-conductor is called an insulator. For example, the plastic around the wire is insulation. There we go. Okay, so what about something called double insulation? Double insulation. Well, with double insulation, it is when basically none of the electric parts of the appliance can be touched by the user. What on earth does that mean? Well, when we have, let's say, a TV screen, right? There are definitely electric parts inside it. Let's make it one of those old-fashioned ones that has like the big box on the back. Remember those? Used to turn them off and then they used to finish off like that. Going back to the 60s, is it? Welcome to the 60s. Oh, okay. So this is a TV. This is our TV. If that, we can make a better TV than that, can't we? All right, let's try again. There we go. Perhaps? Yes? Looks like it's on a pedestal, but okay. We can do with a pedestal TV set on the table. Okay, so this is our TV set. And double insulation is the fact that, well, we can't touch any live wires. And so there's a live wire inside. There's a spark on the live wire. There's a box around it, so that is insulated. But double insulation is when they put another layer around that. So in case if this one comes live, then you can still touch the outer casing without becoming electrocuted because it is neutral. Means it doesn't have any, well, electric charge, it doesn't have anything flowing through it, no current at all, so it's a double insulation. Yeah, so the outer casing of the appliance is also made of an insulating material such as plastic. Earthing, for example, when an airplane is flying, okay, we have physics air again. Physics air with a little light bulb. A light bulb, sorry. We have a car. What do these two things have in common? Well, other than that they are both vehicles, they both move, they both transport things, they are both made largely out of metal. Okay, that's enough of them. Well, what are some other things they have in common? Both of these need to be earthed when fueling. That doesn't mean they need to be on the ground, although that is true. It has a different meaning in physics. So earthing is, well, it's when a plane lands. The plane, this is an example I'm giving. The plane is immediately earthed so that the electrical charges can escape the plane into the ground. And with the car, when it's parked in the gas station, a bonding line is used to earth the aircraft before it's refueled. Why? Well, if the plane or car was not earthed, there is a risk of the electrical charges igniting the fuel. Another example is when machinery operators in factories stand on insulating mats or wear shoes with insulating soles. This stops any charge flowing through them onto the earth. So when you have a car and it's being fueled, you attach a lead to it, sort of, and this takes any charges off of the car, away from the car, so that it can't ignite the fuel. So let's say the car becomes negatively charged. When you get the bonding cable and you connect it to the Earth, this is the mass of Earth. Yes, the car is definitely floating in space right now. So this is the Earth, the ground. It's positively charged. So all the negative charges move in this direction towards the Earth, and they will leave the car neutral. They will move the charge from the car, so that means charges can't jump from one place to the other, and they can't ignite the fuel. So that is what they are used for, the bonding cables and the earthing in these situations. And that's the same thing for a plane when it's parked and it's getting charged for the same reasons. A fuse. A fuse is a safety device with a fuse. So if it gets too hot, because the wire is a low melting point, it breaks, and that breaks the circuit, and that's how it keeps the circuit safe. You also need to know about the circuit breaker. Circuit breaker. And this is found in a range of domestic appliances, and all you need to know is if the circuit overheats, the circuit breaker opens, breaking the circuit. As a resistor slows down the movement of electrons, the kinetic energy that was moving around inside them is converted into heat energy. This can be used in a range of what is called domestic situations, which means situations in the home. A few examples of this are hair dryers. Don't ask me how this is a hair dryer. I don't know. That is my hair dryer. I always feel like that this weird thing on the side. Is it just me? Wait. How does one draw? Okay. It looks more like a gun with a weird shape. Okay, that's the hair dryer. It's the hot air coming out of it. It's like a deformed hair dryer. Okay, hair dryers, kettles, electric kettles, not the old-fashioned one I'm drawing here. Okay, this is an electric one. It's an electric one that's designed to look like the old ones. Look, I'll draw a wire, just so it's as accurate, it looks like a genie lamp, as it can be. Okay, see, it's even plugged into a socket. There, happy. So there is our electrical kettle. And what else do we have? We have ovens, electric ovens. And we have irons. The steam coming out of them. And what else? We have electric hot plates. So you can cook dinner on them. Ooh, it's a delicious aroma of a couple squiggles. Yeah, and basically in all these uses, you could basically sum it up in heating food for this, basically cooking. So that is not a very neat one. There we go. So cooking and boiling water. And then all three of these, essentially all of these actually can be summed up as heating. That's what they do. They heat. A couple dandy equations that will no doubt help you secure top marks. first of all, power. Oh, that's so frustrating when not all the board is erased. Okay, power equals current times voltage. Sorry, it sort of fell off the board there, didn't it? Okay, we'll try that again. At least you'll learn the equation. Power equals current, or rather, it'll be easier for you to learn the equation if you see it more times. Yes? Some of you have probably already memorized it. Okay, so power equals current times voltage. Power is measured in watts. Current is measured in amps. And voltage is measured in volts. Okay, for example, what is the power of a 5 amp and 1.5 volt? Let's see if you can guess what I'm drawing before I've drawn it. I'm sorry if this is a horrible drawing. Ideas? Well, this is a lava lamp. A lava lamp. Might be difficult if you don't know what a lava lamp is, if you've never seen one, but basically a lava lamp is this cool chemical thing where they just get a bunch of chemicals. You put a light in the bottom, it glows in the dark. You can get one that sort of chain shaped. And if we wanted to find the power in one of these interesting contraptions, what would we do? So we would use the equation power equals current. Let's use the units just so it fits on the board. Power. Ooh, let's use a unit. Let's use watts. Power equals current times voltage. That doesn't. Should I use the I there? E. I'll just leave it like that. We'll just use it like this. So it is 5 amps. So you just plug in the 5. Plug in the 1.5, so you get 5 times 1.5. And that gives us a nice 7.5 watts. The second equation is current times voltage times time. So if you're like me and you'd like to see that in a nice straight line rather than in paragraphs, then we would have, okay, there's an interesting thing about this equation, is that, well, we all know that most of the time in GCSE physics, time is measured in seconds. This is not what happens here. The amount of mains electrical energy transport is measured in kilowatt hours. Kilowatt hours. The unit of the power, which is current times voltage in this equation, is kilowatts instead of just watts. So what that means is, basically what kW means is 1,000. K means kilo, like a kilogram or a kilometer, which basically means 1,000 of something. So if you have 1,000 watts, so this is equal to 1,000 watts. So 1 kilowatt is equal to 1,000 watts. So it's a big measurement, let's say, relatively speaking. So that's kilowatt. That is a power. So this is the kilowatt hour. Kilowatt hour. Or rather, the energy transferred This is the power, which is current times time. Oh wait, no, current times voltage. There we go. That's amp. This is volt. And then lastly, we have our time measurement. And we all know it's supposed to be in seconds. It's not seconds here. It is hours. So you can put an H there to show time in hours. So basically this is that one equation that breaks all the rules. To convert from watts to kilowatts, you basically divide by 1,000. For example, 2,000 watts is equal to 2,000 divided by 1,000, so that's 2 kilowatts. Also note that time is measured in hours here instead of the more usual seconds. To convert from seconds to hours, you must divide by 3,600. This is the number of seconds in 1 hour. For example, 1,800 equals 0.5 hours, which is basically 1,800 divided by 3,600. Finally, you need to understand the difference between mains electricity being alternating current and direct current being supplied by a cell or battery. Okay, what on earth does that mean? So we have a cell or battery, in this case a cell, which is one battery, I believe. I may be wrong. That's one battery. If we drew with an oscilloscope here, we'll put the other one for the mains electricity. We'll just draw pylons to represent those. I'm not sure if this is what pylons actually look like. Apologies for any inaccuracies. Well, let's say it's something like that. So this is mains. Mains electricity. And if we looked at the oscilloscope for each of these, then the alternating current with the mains electricity, this is the battery, would look like this. And I will explain why in more detail later. And the cell or the battery on the oscilloscope would basically just come out like this. Why does this happen? Well, here the mains electricity, it's moving in one direction and then it's moving in the other direction, which may be a little bit strange to get your head around at first. The electricity is moving in this whole wire, all this way. It's moving in one direction and then in the opposite direction, and it's doing this at thousands, maybe millions of times a second, and that's the alternating current in the mains electricity. And with a cell or battery, it's just constant. It's always moving in one direction. So if you looked at an oscilloscope, this is what you'd see. This would be the reading. It's a constant flat line. That. This alternating current has some more strange applications, and we'll go over why they are strange and what they mean in a later video. If you found this video helpful, please leave a like and subscribe. And if you have any feedback as to how I can make these videos easier for you to revise from, then please feel free to let me know in the comments.